Hello everyone, I'm Umberto Michieli from the University of Padua, Italy, and today I'm presenting our last paper entitled GMNet, Graph Matching Network for Large-Scale Semantic Segmentation in the Wild. First of all, I'm going to briefly introduce the semantic segmentation task, in which a label is assigned to each pixel of an image. For this reason, it represents a dense prediction task. As in many visual tasks, also semantic segmentation has been revolutionized by the deep learning era, starting with fully convolutional networks and autoencoder-like models. Nowadays, the semantic segmentation task represents a very important problem toward complete machine understanding, and it can be applied into many different fields, from autonomous vehicles to robotics, video surveillance, medical imaging, and so on and so forth. The task we consider is the semantic segmentation of multiple parts belonging to multiple objects. It is a special case of semantic segmentation in which we want to recognize parts of objects. Indeed, given an RGB image, we could have different levels of machine understanding. The most common scenario is the semantic segmentation of object-level classes. However, one may be interested in understanding the parts of a single object, as in single-class part parsing, to better understand the pose or the interactions of the considered class. Here, for instance, you can see the person parts. Instead, we focus on the more challenging scenario of multi-class part parsing, where we want to identify multiple parts of multiple objects, with a high level of details. This problem remains nowadays quite marginally explored, despite its importance toward detailed object understanding. We set up this problem as a special case of coarse-to-fine learning. Indeed, our aim is to transfer knowledge from a coarse problem, the semantic segmentation of objects, to a finer one, the semantic segmentation of parts. We call this spatial-level coarse-to-fine learning, as object-level classes are split into their respective parts, as we can see here where object-level annotations are refined into part-level ones. The first idea that one may come up with is to simply take a standard semantic segmentation network and train it on all the parts. Well, of course we tried this and this works up to some extent, but it does not achieve satisfactory results for two main reasons. The first reason is what we call object-level ambiguity. We think that corresponding parts in different semantic classes often share similar appearance. For instance, if I ask you to determine which ones are sheep legs and which ones are cow legs, it may be hard to say. Maybe some of you could guess it, but if I give you more object-level context, then it's definitely much easier to answer this, right? The second reason is what we call part-level ambiguity. Standard semantic segmentation architecture can capture only limited local context. Again, if I ask you to determine whether this is a dog head or a dog tail, it may be hard to say. Maybe some of you could guess it from the orientation of the fur, but in general, if I show you the complete picture, it's much easier to recognize the spatial relationship of all the parts. Keep in mind this figure, because we will see it again in the results section. So, in order to deal with these two types of ambiguities, we designed three components, which are the main contribution of our work. As regards the object-level ambiguity, we propose an object-level semantic embedding network to guide the prediction of parts using some kind of information prior on the object-level classes. Additionally, we propose an auxiliary reconstruction module which brings parts back to objects, and we will see it in a minute. To deal with part-level ambiguity instead, we designed a novel graph matching module to preserve the relative spatial relationship between ground truth and predicted parts. More in detail, we go now through our complete architecture. We are given an RGB image, and we take a pre-trained, off-the-shelf, object-level semantic segmentation network, which we don't update during the training. Then, we designed an object-level semantic embedding network as a cascade of convolutional filters to guide the part-level decoding stage with object-level awareness. The concatenation happens channel-wise at different resolution of the decoding stage. In this way, part-level features carry also information about the object-level classes at the decoding stage. To train this kind of architecture, we employed three losses. First, a cross-entropy loss to learn the task. Second, we added an auxiliary module which reconstructs objects from the prediction of parts to further penalize parts placed in the wrong object. This is simply implemented as a cross-entropy loss between the reconstructed and ground truth object-level segmentation maps, and it serves as an additional penalty for the prediction of paths outside the corresponding object-level class. Finally, we designed a graph matching module which builds a graph from both the predicted and the ground truth segmentation maps, and aims at matching the spatial relationship of the paths. Going more in detail on the last aspect, we start from the ground truth and the predicted segmentation maps at the part level. For each couple of parts in the scene, we delete the parts and we count the number of pixels in the intersecting area as a weight for a weighted adjacency graph. We do this for each couple of parts in the scene, and then we normalize the resulting metrics row-wise in order to give same importance to large and small parts. This way, we obtain matrices of proximity ratios, which measure the flow from the considered part to all the others. Finally, we built a simple graph matching loss between the two adjacency matrices that we implemented as a Frobenius norm of their difference. The aim of this loss function is to faithfully maintain the reciprocal relationship between the parts. On one hand, disjoint parts are enforced to be predicted as disjoint. On the other hand, neighboring parts are enforced to be predicted as neighboring and to match the proximity ratios. As regards the datasets, we use the VOC 2012 Pascal part, which has about 5,000 images for training and the same amount for validation. It has 21 object-level classes, background included, and we employed two different part-level splits. The first split is formed by 58 parts and was proposed by Zhao et al. At ECCV 2019. The other split, instead, has 108 parts, which we built following some of the rules identified by González Garcia et al. In 2017. So, as regards the first experiment on the Pascal part 58, we can see that standard semantic segmentation methods typically have low mean intersection over union. We started from the DeepLab v3 with less than 101 as the backbone in order to fairly compare with the only other method designed for multi-class part parsing, which is BSA-net. DeepLab v3 has also proven to be the strongest baseline among the compared ones. We can see that we are able to outperform the baseline by more than 4% of mean intersection over union, and the BSA-net approach by almost 1% of mean intersection over union. We can verify the contribution of our proposed modules in the figures on the left. From the first image, we can see that cat head in light green and cat torso in green are corrected into dog head in red and torso in blue, thanks to the semantic embedding network which guides the prediction toward the correct object-level class. You may remember the second image. Well, we can see that the dog head and dog tail are correctly identified thanks to the graph matching module. Again, graph matching helps in the third image to correctly identify the cat tails. When we move to the 108 parts scenario, similar considerations apply. However, in this scenario, the gap is even bigger. We gain about 4.5% of mean intersection over union with respect to the baseline, and about 3% with respect to BSA-net. From the visual results on the left, we can see that sheep parts are correctly identified by our method, thanks to the semantic embedding network. In second row, the cow horns are correctly placed thanks to the graph matching module. And similar discussion also holds for the sofa in the third row and for the potted plants in the fourth row. In conclusion, we saw the challenging task of multi-class part parsing, and we tackle it with three main contributions. First, we proposed an object-level guidance for part-level decoding stage. Then, we proposed a graph matching module for accurate relative localization of semantic parts. Finally, we achieved state-of-the-art results on two public benchmarks. Okay, so that was all, and I leave here some further references. In particular, we have the label mappings available for the two scenarios of 58 and 108 parts on our paper website, and the code is public on GitHub. Thank you for your attention, and we look forward to meeting you in the live session.